Let us continue with our discussion of real analysis or point set topology on metric spaces. Now, last time I talked of the last thing that I mentioned was continuous functions. But before that, I started with the open balls, moved on to open sets and closed sets. Now, in the context of closed sets, there was one thing that I forgot to mention. So let me just add it here as a remark slash definition. You take any subset of a metric space, the closure of S. The closure of S is defined to be the set S with a line on top, S union S prime, where S prime is the set of all limit points of S. Now, the limit point, of course, here I might have used the term accumulation point. They mean the same thing. Some authors use them differently, but for us, limit point equals accumulation point. Right. So essentially, so the point is that even if S is not closed, one can do this operation of taking the closure of S, which is just S union S prime, and the fact is that proposition, the closure of S is always closed. Okay. Well, let me add it as 1. Second thing is, as I mentioned earlier, the closure of an open ball is the corresponding closed ball. Of course, notationally, we had denoted a closed ball by BPR with a line on top. Now, that's just notation, but what this proposition says is that that notation is consistent with this closure notation, because it is indeed the closure of an open ball. Now, let's continue with continuity. So I think this was, I believe, 6. A function f from x dx to y dy is uniformly continuous if the following holds. given epsilon greater than 0, there exists delta greater than 0 such that the distance in y between f of x and f of y less than this epsilon whenever the distance between x and y less than delta. Yeah, as we know, this unlike continuity which makes sense at a point, this essentially is a concept which involves the whole domain. So that's where this the term uniform comes. The same delta is supposed to work for any x essentially. So there's one delta which will guarantee that whenever 2 points are close, their images are close. This is this is a somewhat strong condition. Fortunately, in some cases, it is one can check, as we'll see later on when we talk about derivatives. Or if the domain is somewhat restricted, like if the domain is compact, this holds. I'll mention that soon. So, 7. Compact sets. So let K inside X is compact if. Now I'm going to give a definition. The first the definition, this definition is works only in metric spaces as opposed to general topological spaces, but in any case we'll be just dealing with Euclidean space, so this will do for us. K inside X is compact if the following holds. Any sequence in K has a subsequence which converges to a point in K. Right. So this is called, this is also called sequential compactness. Now, the more general definition of compactness is as follows. Alternatively, an open cover of K is a collection of open sets U alpha, alpha in some index set, is a collection of open sets such that the union of these open sets U alpha contains K. So then the theorem is that K is compact in the sense of sequential compactness if and only if every open cover of K has a finite subcover. Finite subcover. So, well, what this means is that if U alpha is an open cover of K, then there exists alpha 1, alpha, let's say P, such that U alpha 1 union U alpha P contain K. So in this family of open sets, there exist finitely many of these. We don't know which ones, but there are finitely many of these which will already do the job of covering K. In other words, whose union contains K. So this is a theorem. It's not entirely obvious. It requires a bit of work. But I assume you would have seen it already. Now, a crucial ingredient in this is the Lebesgue number lemma, Lebesgue number of an open cover. Now, for now, I won't mention this, instead of which I'll list some properties of open sets, compact sets. There are many, but the trivial properties are the following. The first one is that if K is compact, K is closed and bounded. The second thing is if X is a compact metric space and K is a closed subset, then K is compact. Now, both of these are fairly straightforward, but something which is again, which is non-trivial, and the next theorem is not true for an arbitrary metric space. It is true in Rn, for example. There are other examples where it's true, but certainly true for Rn, is the Heine-Borel theorem. It is a converse to the first statement that I made here, that compact sets are closed and bounded in arbitrary metric spaces. But the converse is true in Rn. If K contained in Rn is closed and bounded, then it is compact. Okay, so then the fourth property is that if f from x to y is continuous, and k is compact, then its image is compact as well. F of k is compact. This is an extremely useful thing, and it will have lots of nice consequences, as we'll see. And the fifth thing is that if x is compact and f from x to y is continuous, then f is uniformly continuous. So at least this gives one setting. This combined with the Heine-Borel theorem will give us, enable us to conclude that lots of continuous functions are uniformly continuous. For example, the Heine-Borel theorem, one immediate consequence is that finite closed intervals in R are compact. And this fifth statement here will immediately tell us that if you have a continuous function whose domain is a finite closed interval, then it's uniformly continuous. Now, in Rn, instead of finite closed intervals, the analogues would be closed balls of finite radius, finite radii, and a continuous function with domain a closed ball would be uniformly continuous. Now let me just change notation slightly, so I'll use circles to denote these. And in my list of concepts and definitions, so this was 7. And then 6. Well, I'm not being very consistent. So here, for example, I would need to use this notation. Likewise here. And another important concept would be that of a connected set. S contained in X is, we say that it's connected if we if there is no separation of S, i.e., so a separation of S is a pair of open sets UV in X such that U intersection V is empty and U union V contains S. So see, the second condition, U union V contains S, is equivalent to saying that U intersection S union V intersection S is actually equal to S. So you cannot break up S into two disjoint pieces such that each piece is the intersection of S with an open set in X. So what we need are, so proposition, so few facts. The first one is, if f from x to y is continuous, and s contained in x is connected, then f of s is connected. This is again, it's a easy thing to check, but the second property is not is again something special, which is that what Euclidean space is, that the only connected, actually only this is only true in R, the only connected subsets of the real line are intervals. So when intervals, I mean it can be a finite interval, infinite interval, half open, closed, etc. Any possible interval is connected, and these are the only ones. And in if you go to Rn, then so yeah, right, the only connected subsets are intervals. That's one thing. Well, actually, let me rephrase this in a better way. Instead of wording it like this, I'll be more explicit. A subset of R is connected if and only if it is an interval. Now using the second one, that intervals are connected, and the fact that continuous images of connected sets are connected, one can conclude that balls in Rn are connected, etc. So more generally, a subset is said to be path connected if given PQ in S, there is a continuous function f from a closed interval AB to S with f of A equals P, f of B equals Q. Such a continuous function f is called a path between P and Q. Now notice that here I said a continuous function from whose target is S. The metric space here is X. I could have said a continuous function from the interval to X whose image lies in S. That's fine. But what I wrote is also okay, because in order to make sense of a continuous function, what we need is the target to be a metric space. Here I'm using the trivial fact that if you have a subset of a metric space, that itself is a metric space. Just use the same distance function on the subset. So S itself can be a space. So what I wrote is a definition of a path connected set. Now, using the first and second properties in this proposition, excuse me, one can check the following, that if S is path connected, then S is connected. This is very useful because the abstract definition of connectedness as that it cannot be written as a separation is not so intuitive, while to show that, especially if you're trying to prove that a set is connected, the natural thing to do is try to take 2 points in the set and join them by a path. And this last thing ensures that if we can do that, the set is indeed connected. So I think we have pretty much covered whatever we need. If I need anything more from metric space topology, I'll mention it in the course of whatever we are doing. So in my next lecture, I'll actually start with defining a a derivative of a function of several variables. So let's stop here. Bye.